At the end of Volume 1, we saw how a modern flame retention burner uses the principle of atomization for an efficient, clean flame. But the burner is just one part of an efficient system. For example, the combustion chamber must surround the flame and radiate heat onto the flame envelope to help it burn the oil completely. Next, there's the heat exchanger, which forms a wall between the combustion chamber and either the air in a furnace or the water in a boiler. You learned in Volume 1 that heat is a byproduct of combustion. Other byproducts are carbon dioxide and oxygen. They, along with water in the form of superheated steam, pass up the flue of the heating system and into the chimney. The heating system may also require fresh air intake from the outdoors, temperature controls, and sometimes draft regulation devices to make it fully automatic. For a heating system to perform efficiently, every component must work in harmony. Combustion chambers can come in many sizes and shapes. When an old-style combustion chamber has a profile like these two, and old-style non-flame retention burners are used, there will be some cooler corners and surfaces that the flame does not fill. The result is less rapid evaporation and incomplete combustion of the droplets. Modern flame retention burners are less affected by variances in chamber configuration. The secret of high fuel efficiency is complete and rapid burning of the fuel oil, so the chamber ideally follows the shape of the burner flame and reflects heat back into the flame. There are two types of materials commonly used for combustion chamber refractories. Fire brick has been used from the early days of oil combustion. The bricks, or hard-cast chamber surfaces, provide refractory that is durable and can operate in the 2300 degree Fahrenheit temperature range. The second material is a soft refractory material typically made of alumina silica fibers. This material has an operating range to 2300 degrees Fahrenheit. Here are three combustion chambers made from soft fiber refractory material. The material makes it easy to achieve a chamber with few or no corners and without cool surfaces. Soft refractory chambers also offer fast temperature rise from a cold start, uniform flame temperatures during steady operation, sound insulation of the combustion noise, protection from intense heat, and rapid heating-cooling cycles. But what about an appliance like this? It's a wet base boiler where the burner is fired with a target wall. Here, flame temperatures can be as much as 200 degrees to 400 degrees cooler because heat is radiated to the surrounding water-backed surfaces, providing excellent heat transfer. This is a dry base boiler. The combustion chamber totally surrounds the flame. Oil droplets are completely burned within the chamber. Hot gases exit at the top to give up their heat to the surrounding heat exchanger surfaces. Since the combustion chamber contributes to the complete combustion of the flame, it is sized to match the firing input of the nozzle to provide the amount of heat needed by the particular job. The physical size of the chamber in most residential applications is based on the square inches in the floor of the chamber. 80 to 90 square inches is normally ideal for a 1 gallon per hour firing rate. Chambers can be quickly repaired using this packaged ceramic lining kit. It comes out of the box wet and flexible, so it's easy to install inside a chamber and mold to fit the chamber shape. When the chamber is fired, the material becomes rigid. Sizing data for square, round, and rectangular chambers is available in a convenient chart. It also gives the ideal wall heights based on the burner firing rate. The burner end cone should be positioned about 1/4 of an inch back from the inside chamber wall so that the combustion head and air tube will not become overheated by recirculating hot gases during operation. In some relatively hot applications, refractory fiber material should be placed around the outside diameter of the burner end cone and air tube to provide insulation from radiation and overheating. When insulating material is not available and the chamber opening is larger than 4 3/8 inches, the burner end cone setback should be increased slightly, but care must be taken to avoid oil spray impingement on the entry walls. The heat exchanger takes the heat, but none of the gases or other byproducts of the combustion, and transfers it into either the air inside the ductwork or the water in a boiler system. There are 3 things that influence the rate of heat transfer: temperature differences, contact time, insulation. By keeping the temperature high on the combustion side of the heat exchanger and by circulating the air or water on the transfer side, maximum heat is drawn into the air or water. By increasing the surface area of the heat exchanger, more heat is drawn into the air or water. Lowering the excess air used in combustion also increases contact time, since a smaller volume of hot combustion gases is produced. This chart shows the relationship between the volume of hot combustion gases and the temperature of those gases when excess air volume is increased. Note the temperature is reduced as the air volume is increased. Insulation is the last thing you want between the combustion chamber and the heat exchanger. But that's exactly what you get with soot buildup. It's estimated that 1/8 of an inch of soot is equal to 1 inch of fiberglass insulation. This is why heat exchangers should be cleaned annually. Draft is the word we use to describe the slight suction that lifts the byproducts of combustion up the chimney to the outdoors. Natural draft is the result of hot gases rising. By putting the hot gases in a narrow, high chimney, the gases can be made to rise faster. Torrential draft is the suction in the chimney created by winds that blow across the top of the chimney. In addition to wind, draft is also affected by chimney height. The higher the chimney, the greater the draft. The temperature of the gases. The hotter the gases, the greater the draft. The coldness of the outside air. The colder the air, the greater the draft. With wide draft variations come some very serious combustion problems, including increased smoke when too little draft reduces combustion air, poor operating efficiency when too much draft draws too much air into the combustion process, reducing CO2 and raising stack temperature, heat loss during off periods due to high draft drawing heat up the chimney. The best way to minimize draft problems is to use a draft gauge to measure draft intensity when setting up the burner. Take the reading with the burner in a cold startup condition. That's when there is minimum draft. Set the burner for zero smoke combustion with a reading of -0.01 to -0.02 inches of water as shown on the gauge. At this setting, the burner will generally have adequate draft under variable conditions. Next, you'll need to have some way to regulate the draft so that it stays near its ideal low overfire draft condition. Here are some of the draft regulators available for maintaining the -0.01 to -0.02 inches of overfire draft. They all use a swinging weighted door for regulating the draft by allowing air from the room to enter the flue in the chimney, rather than pulling too much from the combustion area. Begin by taking an overfire draft reading. If the draft is higher than what you prefer, or that specified by the appliance manufacturer, adjust the regulator weight to allow the door to open more. If the draft is below -0.1 inch, adjust the regulator weight to just close the regulator door. If you cannot reach the -0.01 inch reading, a draft-inducing fan may be needed. The second draft measurement should be taken at the breech or stack connection. Here the measurement should be slightly higher than the overfire draft due to the pressure drop or resistance across the heat exchanger passageways. But the draft doesn't work alone. It is influenced by the flue and the chimney. Size the flue pipe the same as the breech connection pipe. Use a minimum number of elbows. In this variation, the draft regulator is installed in the flue pipe between the appliance and the chimney. Regulator pipe diameter should be at least as large as the flue pipe diameter, unless specified otherwise by the manufacturer. The pipe should rise 1/4 inch per foot in the flue run to the chimney. Chimney material is usually brick, but special alloy metals may also be used. Both types require periodic inspection. When you find unusual conditions, tell the homeowner. A chimney repairman should correct any problems. Now you should have a good idea of what to look for from the burner to the top of the chimney. But what about the oil supply system? How does that affect burner performance, and what can you do to assure adequate oil delivery to the heating system? Well, you'll explore that subject in Volume 3, entitled From the Tank to the Nozzle. This video training library is produced as a service to the oil heat industry by R.W. Beckett Corporation.